A special welcome to the last video of the Advanced Algebra 2 Summer Bootcamp series. This is the last topic, number 8, exponential functions. And if you've watched all of the video lessons leading up to this one, way to go. And thanks for being patient with me and learning with me through the whole deal. So let's get organized for this very last lesson. We'll need these two documents. We have the lesson page and the TI activity page. And of course, we'll need your TI-84 calculator. So let's jump right in and get a little background information of exponential functions. So the first thing is, well, what is an exponential function? And by now you have some familiarity with how exponents, work out. So the official definition would be a function that can be written in the form f of x, or y, is equal to a times b raised to the x power. Now this model wouldn't make much sense if a was 0. It would just be 0 all the time. So a is not equal to 0. And it also wouldn't make much sense if b was equal to 1. Even 0 would make sense, but officially we say b is not equal to 1. Otherwise the number wouldn't change either. It would just be 1, 1, 1, 1, 1. But b can be greater than 0 and less than 1, so a fraction, or greater than 1 so that the exponents grow, or the values grow of the exponential function. So that's it. So it's in that form. There are some other things, but we learn it through looking at the data. On the right here, how about exponential functions on the TI-84? I graphed 3 of them. I believe they're 2 to the x, 3 to the x, and 4 to the x. So 2 to the x would be the one farthest to the right because it grows the slowest out of the 3. But what's unique about the graphs on the calculator is that they all 3 pass through the point 0, 1. And that could change based on the values of the initial values and stuff like that. But usually if we just start with 1, if you plug in 0 for the exponent, you'll always get 1. And that's it for that. The next thing is evaluating exponential functions, which isn't much different than evaluating quadratic functions or linear functions, but I want to touch on it again because it's a really common thing. So like other functions, we do one of 3 things. We either look at the table. So we go to we have the function in y equals, and we press second graph to go to the table. We could evaluate on the main screen using the button alpha trace. So we did that in the last video. But then this visual that I showed you here is how to do it on the graph. So step number 3 is, or option number 3 is graph. So looking at that graph, the way that I got that little x equals at the bottom there is I pressed second trace, which is the calculate feature, and then chose value. And that allows me to enter any value I want to. So that's helpful if we have the graph up and we want to see that point pop up. So once again, second trace, value, and then you just type the value that you want to evaluate at. And then what's cool is the point will show up on the screen, and it will save the values in x and y, like I've shown you before. Exponential modeling. Okay, so we've done linear modeling already and a little touch on quadratic modeling, but so exponential functions are used to model a few different things that come to my mind, at least. Bacteria growth. Makes sense. It grows exponentially. And then population growth. If you look at a graph of our population of births, it has a curve to it. And then the spread of a virus. In this lesson, though, we'll talk about a computer virus. Whew, I don't want to get into that conversation right now. Okay, now the 3 things that we do, remember, to regress or model in that process is first we enter data. So it's the analytical part. Second, we model the data. So it's coming up with a curve that fits the data. and then 3 regress. We make that official regression, which is projecting values. So we'll do all 3 of those things in this lesson. So the screen on to the right is just showing you the option that we'll choose for exponential regression. That shows up when we press Stat, Calc, and then we just arrow down to the 0 for exponential regression. I think it shows all the way up to ln or ln. Right above exponential is ln, which is natural log, not linear. Okay, so that's the background information. The next thing that we'll do is check out the TI activity page, and I'll walk you through those steps on the calculator. Spreading doom. Student activity. Modeling the spread of a virus. Okay, we're talking about computer virus here, so don't freak out. But let's go over the setup here. At 8 a.m. on January 26, 2004, the MyDoom virus was released. 6 days later, over 1 million people reported that their computers were infected, and MyDoom was named the fastest spreading computer virus ever. In this activity, you'll explore how the virus spreads so quickly and derive an equation to model its spread. So let's discuss, some one-sided discussion, how the virus spread. And this is pretty common. Like, you could get an email from someone you don't know, or maybe someone you know. There's an attachment or a link, and you click that attachment, little mini app that installs on your computer, and then it copies itself to email addresses in your contact list, spreads it to them, maybe guesses what other names are at a certain website, and then that would repeat based on all of those people's contacts. Yikes. That could spread very quickly. There's also an example of chain emails. So when you get the email, it's got like a joke or something funny or something, if you forward it, you get luck. And so you send it to 5 closest friends, so then 6 people have seen the email based on the first person who started it. Then those 5 send it to their 5. So 5 times 5 is 25, plus the 5 and the 1 is 31, and then it continues and continues. So the MyDoom virus was like a chain email that forwarded itself to your closest friends and thousands of other people you didn't even know, but nobody knows how it spread actually. But we have some data that's on this page here. We have the 0th hour, the 1st hour, 2nd hour, 3rd hour, and how many emails were sent. So first column is number of hours since the virus was released. Second column is how many emails sent by the virus in that hour. So the question 1, not very mathy, just how do you think the virus spread? And it could be like the chain email above, or it could be like the general way that a virus spreads with an attachment. But nowadays there are really short links that come from people you know, and it kind of seems like they shared it with you. So it could be something like that. With number 2, we're finding the common ratio. So I'm going to the calculator, and I'm taking the first 2 numbers, 10,800, and I'm dividing it by the first number. So I could see how we get from 6,000 to 10,800. So we multiply by 1.8. So it's like a 1.8 rate. Now I take the third one, 19,440, and divide that by 10,800 and see what that rate. How do we get from 10,800 to 19,440? And that's a 1.8 rate. So we're expecting that 34,992 divided by 19,440 is the same. And it is lovely. We have a nice activity that's set up fairly neatly. So 1.8 is the common ratio. That means we could find out the future values of the number of emails that were sent by the virus. So what's the rule to find the next term of the sequence? Well, a sequence is just a list of numbers, by the way. To find the next one, all we have to do is take that 34,992 and multiply by 1.8. So there we have approximately 63,000 emails. Yikes. So we could keep going with this. So let's do that. Number 4, how many emails were sent in the 10th hour? So let's see, the first hour is 10,800. Second hour, 19,440. Third hour, 34,992. This is the 4th hour. So let's do this. Multiply by 1.8. 5th hour. Then press enter. 6th hour. 7, 8, 9, 10. So sometimes it's hard to keep track of that, but as long as you keep track of your clicks or your enter button pushing. So that number right there is in the millions. So it's 2,142,000 emails. Holy smokes. Okay. Now what we'll do is let's go to our stat edit, our list screen. And let's just enter the information in the table. We could enter more if we wanted to, but so 0 through 3. So remember stat edit, and then I'll arrow right and just enter those other numbers. And then 19,440 and 34,992. So we're about to plot this on a graph so that we could see what's going on with the numbers and answer this next question. But if we don't have enough information, we could plot more points. So I'll turn on the stat plot. So second y equals plot on. Wonderful. And then, I just want to switch things up a little bit. So I'm going to go with the plus sign. And I'm going to go with red. Zoom. 6. Oh my goodness, the data's not there. What's happening? Ah. Zoom. Stat. Number 9. Awesome. Okay, that means I could do something with this. Like I have some data that's curving upward. So if I were to sketch a curve, it would be kind of opening up. So to answer that next question, describe the shape of the scatter plot. Well, the scatter plot is curvy and it's opening up. And we could really describe this as an exponential shape. But we're just learning about that. So great. On number 6, what we're doing is completing the table to find a function to model the spread of the virus. So we'll do this just kind of audibly here, and then we'll model the data with the calculator. So notice in the first row of the table, we have 6,000 emails. And then to find the next one, we have to do 6,000 times 1.8, so the second row. And then we have to do 6,000 times 1.8 times 1.8, so twice. So the pattern flows that if you're finding x equals 3, there should be multiplying by 3 1.8s. And then x equals 4, there should be 4 1.8s. So what that allows us to do in the far right column is to write that kind of whole model as a really simple setup using exponents. So there'll be a 6,000 as our initial value, what we started with in the equation, every single one of them. And then depending on how many hours we go, that's going to be the power that we raise 1.8 to. Because 1.8 times itself 3 times or 4 times is the same as writing it in an exponential form. Super. So that table is really helpful to figure that stuff out. So the next thing we'll do is let's take this data that we have, and this is really not on your sheet, but this is a really good way to answer number 7. So let's go to stat and then calc, and then arrow down. We did the lin reg before in a previous video, and let's choose exponential reg, EXP, which is 0. So we have our list that we worked with, and we don't usually use frequency list and then store regression equation. So let's click alpha, trace, y1. Enter, enter. Bam, we got our model. And this is the second part of the regression process. Step 1 is entering the data. Step 2 is creating a model. And then step 3 is projecting or regressing what a future value would be. So a times b to the x. So the a is 6,000, just like in our table. B is 1.8. And then we raise it to whatever hour it is. So now we go here to y equals. And we see, like, this is kind of crazy. This is pretty much 6,000. Okay. So we'll leave that there, and then second right, we'll go to the end, and we can see that it's 1.800000003. So not perfect like we wanted, but so that will show up on the graph right through the data points. Okay, then in a moment we're about to regress or project, so we'll do that. But in number 8, the function is an exponential function in the form a times b to the x. Explain what the values of a and b represent. So I'm clicking trace here. Notice I'm on plot 1. I'll go up and then arrow to the left where x is 0. Well, a is the original amount of emails that were sent, like the virus, you know? And that applies to all sorts of situations like bacteria. If at time equals 0, there was 1 bacteria, then that's the original amount, and then at time 1 minute later, there'll be 2 bacteria or something. And then B is the rate at which the virus is spreading, bacteria is spreading, population is spreading, and that's called the common ratio. So, you know, if I go to that next point, we would see that, oh, the way that we get to that number is multiplying by 1.8. So we wouldn't see that on the graph, but we know that based on this number. Number 9, use the function to find the number of emails sent by the virus in the 144th hour. Okay, we're going to try this on the calculator, but notice that 144th hour, that's like way down in the future. So I'm clicking window, and I'll do my X max as like 150. But what we're going to see is that the Y values are so crazy big that you wouldn't really be able to see it. So first I'll click, well, let's change the X scale to 10. So graph that. So notice how big that gets. Oh my goodness. That means no matter what we put in for our Y value, like we have put in a crazy amount. Like we know we hit 1 million before and 2 million before. So let me do like 10 million. 10, 1, 2, 3, 1, 2, 3. Like even that doesn't even get close. So really what we're looking for is, this is kind of where we want 144. We need the graph to be over here. So this is way too big to do on the graph. So second mode. Now since we have in y equals the function, we'll do alpha f4 and evaluate and type in 144. So that answer is going to be the number of emails with the virus that were sent in the 144th hour. And that may look like a small number, 3.45, but it's being multiplied by 10 to the 40th power. So that means there are 40 zeros that are put after that 3. So 3.4 times 10 to the 40. Oh my goodness, that's an insane amount of emails. The question though is, does that number really exceed the number of people or email addresses in the world? So there's a point at which this number wouldn't actually make sense. And that's what number 10 is all about. Models often work well for a limited range of inputs. So what are the real world limitations of the exponential model in this case? Qualitatively, meaning not about the numbers, but how would the real world shape of the scatter plot look if the horizontal scale were extended to 144? And then how about the chainmail example? So my first thought is just sketching what the graph would look like based on the fact that we would run out of email addresses for this virus to send to. Like it'd have to double up and go back to other people that it was already sent to. So it would increase like crazy for a bit, and then it would start to level off, which is kind of the case for like bacteria in a petri dish. It'd be limited to with the space that it had, just like the emails would be limited to how many people or email addresses actually exist. So then the other question is, how would the real world shape of it look? So like I said, it would kind of increase for a while and then level off. It would eventually approach one specific number and can't get any bigger. And then just something to think about. Can you think of other examples of exponential models? I mentioned a few. And then how would they be limited? So one that comes quickly to my mind is just the number of people in the world. And our population keeps growing exponentially, but then we're limited by the resources on the Earth and the space on the Earth. So that's it for this activity. Thanks for playing. Not much time. Oh, that's it. That's all the time I have. You probably have things you need to do too. So I just want to thank you for watching this video lesson and being a part of the series. I mean, look at all of the things that we accomplished together. All of these pages. It's amazing. Thanks for putting in some work with me, learning with me, and maybe I'll see you in another video. Or you see me. Do I see you?